can start.
Cool. Hi, I'm Ollie. I've been working here for the last 3 months on the Rust compiler, which you can see with the R symbol. I'm going to talk about existential types, which was a topic I've not heard about before I started, really, and trying to figure this out, so I put it into very grokkable terminology. So yeah, let's start with a simple case. So sometimes you have functions, and sometimes functions should be returning values. And here's a very simple example of a function that returns an integer. And this function will always be returning an integer. Especially, it will be returning an I32. So its signature is a function that returns an I32. Now, sometimes we want something more complex. For example, we want a function that can return any type. In this case, we want a function that takes a value of type t, and returns another value of type t, or maybe the same, but it's still type t. So we know this function always returns a type t. So its signature is, for all types t, there exists a function called foo, which takes a t and returns a t. In normal terms, this means for all possible values of t that you can possibly have, even types that you invented yourself, this function will exist, will take your argument, and return either the same or another value of that type. Now, as an intermediate step to something I'm going to explain in the next slide, let's try to return a value that is heap allocated. So we have a function that returns a box I32, so it's a heap allocated integer, and it will always return a box of an I32. It will always return a heap allocated I32. Now, sometimes we want to return something that just has some specific feature, not necessarily a concrete type, but just something that has a specific feature. For example, it's displayable in this case. Displayable means you can print it on the command line with println. So we have a function that returns a box display, and internally we choose a concrete type, for example 42, which would be I32. But the caller of the function has no idea what the actual underlying type is. We can choose this at random. And we can even choose this, like, depending on arguments, we can return a different type each time. So the signature is, there's a function which returns a specific type on the heap, and all you know is that there exists some type in your type system which implements display. That's all you know. And if the function successfully returns, you know there's at least one of these types, and you got it. Well, one of them. So this is a little bit more complex to put in normal words, but you know the function foo exists. There's no conditions. The function foo exists definitely. And when you call it, you know you at least get a valid value back that implements display. You don't know anything else about the value. You only know it implements display, and you can print it on the command line. So here I made a small table of things that are currently working. We have heap allocated returning a concrete type, heap allocated returning a arbitrary type that we don't actually know, but we know some features about it. We have stack allocated returning a concrete type, but we don't really have returning any type on the stack. So now into existential types, or specifically the impl_trait feature. Impl_trait, here you can see it as the return type is an impl and then the name of a trait, allows you to do basically the same thing you did with the box. So you hide what the concrete type is, but you can still return the concrete type. So the user won't know what the type is, you know what the type is, and all the user knows is display is implemented. The signature is there exists a type t which implements display, and for that concrete type t, this function exists. Note, this is slightly different to what we had with the box. The box had the existential modifier in the back, which means basically that with the box case, you can return different values every time you call the function. With the impl_trait, you need to return the same type every single time. We'll get into the details a little bit later. Let's put this into normal English first. There's one concrete type T. You don't know what the type is, but you know this function is callable and it will give you an object of that type. So we've filled out our matrix. Everything's good, right? Well, not quite. I have a small example that's going to be problematic. So we have two functions that return impl display. And now if you look right here, there's a variable x, it's mutable, and we assign it the return value of foo. So we get this 42. And we don't know that. We just know it's a type that implements display. And if we try to reassign x with the return value of bar, even though they're both the same type, we don't know that on the outside. All we know is some type implementing display. So what you get is a compile time error telling you expected an anonymized type, but you found a different anonymized type. If you look at the existential syntax, this gets pretty obvious pretty fast. It's like there exists a type T for which foo exists, and then down there exists another type T for which bar exists. So it's different types. Well, if you want to use the same thing twice, you should give it a name. As like, this is basic deduplication modular logic. So let's make it possible for Infiltrate to have actual names. Let's first look at how other languages did it. For example, C++ has this really weird declaration where you can make the return type of one function be the same return type as another function. And you're basically stealing types around by using generics, and it gets complex really fast. We try to do this in a more structured way. So we have a named existential type. This is not syntax that's going to be in the language. This is basically just placeholder syntax, which works on the compiler right now, but we want to remove it. It's just the syntax that we could all agree on that we don't want to have. So this is an existential type here. Existential type foo, and all you know about this type is that it implements display. And now you can use this foo, because it has a name, in both of these functions. And since both the functions have the same type, this actually compiles. And since foo and bar both return the same type, we can actually have a variable and change the value by calling a different function that returns the same type. So now we have one existential type foo that implements display, and both functions are under this one existential type. So before we had, remember we had two blocks where it was existential type T implements display, and then we had foo, existential type T implements display, and then we had bar. This time we just have a single existential declaration, and both are under this declaration. So we're basically simply allowing to put both functions under the same modifier, quantifier. Yeah, so back to normal English terms, there exists one concrete type foo for which both of these functions are callable. You just don't know what the actual type is. So the last 3 months have basically been a perfect example of the 80-20 split in implementation effort. The first 4 weeks I've been doing just work trying to figure out how all this types resolution works in the compiler. I've been documenting some of it, and I've been refactoring it to make it a little bit more easy for me to work with. The next 4 weeks, I've been transforming Infiltrate, into something that looks already more like the existential types we have right now. So we're basically generating an anonymous existential type every time you use Infiltrate in the argument return position. And I've also learned a lot about how generics work, which I'll get back to in a second. So after that, we had the 8 weeks of figuring out how stuff works. Then I took 1 day and implemented existential types. And that was it. I had existential types working without generics. We'll get into why generics are complicated in a moment. But simple existential types worked by just using whatever I did the 8 weeks before and implemented it. After that, I spent the rest of the week figuring out how generics work. And the last week, I've basically been writing some tests, doing some bug fixes, and writing some documentation about how all this stuff works. So what was the thing about generics? Well, let's start with Infiltrate first. Infiltrate is converted into existential types in the background. So if you have this example here, where we have an foo impl trait for specifically impl display. We create a secret type. Well, I named it foo here, but like this is not a nameable type. You cannot name this return type. But the compiler internally can figure out, okay, this is a foo, and this function returns a type foo. So we're basically simplifying the impl trait code by making it the same thing as an actual existential type, which is merging it in the compiler, making the compiler itself a little bit more simple. With generics, everything gets a little bit more fuzzy. So if you have a function which is generic and returns a value that actually uses the generic in the background, we need to create a generic existential type, because we need to figure out all the generics that are used inside of this type. So in this example, everything is pretty fine. We copy the generics from the function onto the generics of the existential type. Well, generics aren't necessarily evil, but like people can do very evil things with generics. So let's start with a very small example. So if we have this function t, function foo, which takes a generic argument of type t, and which implements deref and some other things, we need to duplicate this entire trait bound. We need to duplicate the deref target equals array of 3 elements onto the existential type declaration, because all the generics need to match up between the function and the existential type. So if we go a little bit more complex, we can make this length a block instead of having it just be a number. And then we can start putting stuff into blocks, because in Rust, blocks allow you to do all kinds of things, like, well, indenting them and then putting in some statics or something. So if you start duplicating this entire trait bound on type T, you start duplicating the static that's in there. Now this is just like a simple example that shows where it could go wrong. There's lots of other places that are not as stupid as this example that actually would be problematic, but they would be a little bit bigger, so I don't show them here. So duplicating statics is probably not a good idea. And so there's all these questions about what we are duplicating if we are copying the generic bounds of the function onto the existential type. Yeah, so we're basically punting on that, and there's still some compiler magic around impl trait, so we're not duplicating anything. In the last few months, I learned a lot about how the trait resolution works in the compiler. I had no idea about that part of the compiler at all. Then name resolution for figuring out, for example, where the existential types are placed. Like if you name an existential type in the return position, how to figure out where the actual definition is. I learned a lot about that. That's not quite trivial inside the compiler. And also, for the impl trait, you generate a new existential type, which means you generate some definition. And generating definitions inside a compiler is a little bit more complex than just saying, hey, I have this new item, please add it, because the compiler assumes at some point that all the definitions exist already. So you have to have some chicken egg problems here that I learned about how the compiler handles them. And one thing that I also did learn, or kind of relearned, documentation really, really is important. The whole impl trait stuff was very underdocumented, and I documented it now. And it took me quite a while to figure out where all the parts of it were. And yeah, so that's pretty much it. Any questions? Okay, so there's a few. Okay, so the question was like I specifically mentioned that the existential type syntax is a placeholder that's not going to be in the final compiler, and the question is what I think would be the final syntax, or what options are there. And well, one option is to just name it abstract type, which some people seem to like. Another option is to use something completely different. For example, reuse the type alias syntax. So instead of writing existential type T colon some trait, you would write type T equals impl trait. So you would be reusing the impl trait syntax. There's been some confusion about that, whether that would be confusing for beginners or actually easier for beginners, because people have actually been trying to use the syntax just because they assumed it would work. So there's a lot of discussion going on there. I think some people actually opened RCs about that or writing RCs about that. And there have been pages and pages of discussion on Discord about that. I basically ended up eliminating all discussion about it on my PR by saying I implemented the placeholder syntax from the RC, and nobody agrees with it, so we're all fine. Yeah, there was a big bike shed about to start on my PR. The question was how much of this work landed in tree. All of it, like 2 days ago. So we don't have existential types in associated types yet. What you can do, you can define an existential type outside your trait, and in a trait impl, you can actually use the existential type as the associated type, and then, for example, in the return position of an associated method. But declaring it inside the trait impl is not possible yet. So this is a feature that's requested by the RFC, and that I'm kind of figuring out the kinks about it. It's a little bit complex, but yeah, we should be able to do it. Like, it's not problematic to actually end up doing it. It's problematic getting it right with all the generics around and so on. Okay, so the question was what the semantics around that would be. So imagine if you have a trait that has an associated type and a function that returns a value of that associated type. So example, iterator. Iterator has an associated type item and returns an option of that item. And if you implement iterator for your own type, the idea would be you would write, instead of type item equals some concrete type, you would just say existential type item in the trait impl. And then the return type would be figured out by the implementation of the next function. And this would be basically the same thing that's already happening right now, except that you could start returning closures and such things from the next function. So it's, yeah, the only new feature of that is that you can actually do the same tricks like you can do with impl trait by returning unnameable types or hiding types.
So will that associated type be able to depend on the generic type parameters of the impl? Because that's like associated type constructors, right?
Associated types are already allowed to be generic, so we would need to allow that, yes.
But there's a problem with like impl trait returned in trait impls because of that, right?
There's probably a lot of kinks in there that we need to figure out, but I currently haven't wrapped my mind fully around that. Cool. So I guess we're out of questions. And Ricardo, can you end the recording?
Sure.
Thanks.
See you later.